Hello everyone, my name is Tim. I'm the principal cloud developer at S-Cube. Since about July, August, thereabouts, we've been playing around with Graviton2, which is, of course, AWS's implementation of the Neoverse N1. And we've been using it on our main workload, which is almost entirely consists of a finite difference PDE simulation that we run over and over again. And I think we have some pretty interesting results that we'd like to show you. A bit about what we do first. We are a startup that's spun out of Imperial College London. We specialize in building very detailed, very fine-grained Earth models from seismic measurements at the surface. And that's mainly driven by a PDE-constrained inverse problem that we solve. And there's a name in our field for this method. It's called full waveform inversion. And usually when I'm trying to explain it to especially younger people, try to use the analogy of training a convolutional network with videos as input and output. It's sort of about the same kind of data volume that would be involved in the same amount of parameters. Although full waveform inversion, of course, basically 10 years earlier than any of the video convolutional neural networks. So it's been around for quite a while and sort of predates a lot of the modern machine learning frameworks and lingo. So much like a machine learning training job, we have a prediction, which is our seismic measurements. You can see at the top. This is actually a time space plot. So the vertical axis is time, starting from the top to the bottom. The horizontal axis is actually each pixel in the horizontal axis is a particular microphone. And each vertical column of pixels is sort of a time series of microphone response, which is usually pressure response. That's what you see in the color here. So this is an array of microphones that you collect over some time frame. That's basically the data that we collect. That's the prediction that we have. You can see on the bottom, we start out with a very simplistic Earth model. The colors are p-wave velocity in the Earth, which is mainly the attribute that we're interested in. And we produce a prediction, we compare it to the observed data, we get some correction via our loss function, and then we backpropagate it to get a correction for the model. We add it to the model, and then we rinse and repeat, just iterate over and over until hopefully at the end your Earth model gets more and more correct with all these details. All these anomalies that you can see pull out from these kind of measurements, and then your predictions hopefully will match the field data minus the noise, of course. One of the interesting quirks is that for most PDEs, a backprop can actually be produced using the same code as the forward simulation, which basically just means that we have one code base that we just run over and over again. For almost 99% of the time that we're doing this workload. And that is, of course, a solid body continuum wave equation solver. And that is almost entirely our main operational cost, comes from computing that. So a bit about our production code, finite difference code. It's based on, it's not finite element, it's finite difference. It's based on it works on single precision floating point. It has a numerically optimized stencil to minimize numerical dispersion. It's really difficult to compare it to an actual spatial order, but I think it's probably around 12 order. But it's more compact than a 12 order stencil. But the trade-off is that you lose accuracy on some other areas, but that's not usually important. And it mainly computes acoustic and anisotropic effects. And of course, that's sort of chosen to be sort of, trading off from what we need to actually accurately simulate in physics. Sometimes we need more complicated physics, so our code will have to change a bit. But most of the time, we're halfway sort of in this regime. So of course, physical complexity often maps to operational intensity when you're doing physical simulations. So in our case, we're mostly sitting somewhere in the middle in terms of operational intensity. We're neither too memory bound nor too compute bound. We're sort of somewhere in the middle. And interestingly, and I'll delve into this a bit, this code actually has both hand-tuned SSE and AVX implementations. And that's because back when this kernel was being written, AVX was just being introduced, and the implementations are largely very immature. So we made an attempt to write both hand-optimized SSE and AVX versions, and the idea was that whatever hardware that had available at the time, we would try out both the SSE and the AVX versions and see which one actually performed better. A lot of times SSE code would actually perform better, and then we just use that for that particular problem. Now fast forward, a decade or so, the SSE codepath is still in there just in time actually for Neon to appear, for Neoverse N1 to appear with its 128-bit glory. So what is old is new again, but that just means that for us, we have a 128-bit version that translates very easily to Neon, and we can actually compare that to a AVX implementation for Intel. So we can actually have a much more apt comparison compared to a lot of code bases out there. And we don't actually even use very complicated SIMDe instructions. So you can see in the bottom, most of the stuff that we use are just very simple instructions. And for the AVX front, a lot of the actual variables are stored as 128-bit variables. They're sort of packed in there. And so there's actually a lot of just concatenating two variables together and then doing 256-bit wide instructions on that. So they don't deviate too much away from each other. There is some interesting shuffling and some integer unpacking that we can do on AVX2 that we sort of take advantage of, but that's pretty much most of the differences. In terms of actually compiling it, I think the main lesson is that SIMDe everywhere was awesome, and we mostly just had to include the headers and they all just compile very beautifully. Especially if you turn on the macro definition to just keep all the AVX SSE names as is. For compiler, we used a freshly compiled GCC 10.2. We find that GCC 10 actually gave us about 10 to 20% faster code compared to GCC 9, so there actually is a lot of performance optimizations that we can tell happen there. We run it on Amazon Linux 2, which is CentOS 7 based. Actually, I've found out that SIMDe everywhere actually just delegates the shuffle and the prefetch instructions. That's everywhere in our code. It delegates to the GCC's built-ins. So hopefully GCC does a good job of mapping it to the load store architecture, but there's actually so much prefetch hints in the code that I suspect most of the time it's operating with Intel very much like a load store architecture anyways. That's one of the interesting bits. Mostly testing this on AWS's EC2 instances. Now in terms of snafus, we did hit some. So at the very beginning, we saw like these numerical artifacts that come in at later time. They are about 5% of the values, like the median values that you see in this wavefield. And you see this circled in green compared to the reference on the right, which is computed with Intel. There's just some weird sort of straight line artifacts that we can see. And after a lot of testing and debugging, we found that is actually toggled with the FP contractions. So if we turn off floating point contractions in GCC, which is actually known to be very aggressive, this basically means that we can't use fuse multiply adds and all that kind of stuff. At least not automatically. So once you turn that off, that artifact goes away. However, even more strangely, this artifact only showed up in SIMDe 0.5. When we upgraded to 0.6, it actually completely ran away. So I don't know what happened there, but if you are using SIMDe and you're using GCC, watch out that your FP contractions isn't giving you sort of numerical artifacts and making your unit test fail. Okay, so up to the benchmarks. So you mostly care about runtime, right? Because we are a sort of a commercial enterprise here. So, and we're running on a cloud. So actually, faster compute, it means cheaper cost for us because we pay by the hour for these compute. Cache use, you can see that the cache use per thread is one of the main things that we plot out in this graph. It's one of the main variables that we tweak when we are sort of tuning things for new architectures. This mostly corresponds to the cache use corresponds to sort of the tile size that will end up being used for each thread. So there's like a domain composition thing that goes on for multi-thread. So So the cache basically just tells you how big a tile you can use. What we see, well, okay, so first, all the orange stuff is all the ARM scores in Graviton2. The dark orange is the AVX2 translated with SIMDe runtimes, and then the light orange is the SSE runtimes translated with SIMDe everywhere. And we can see like a 15% performance penalty sort of very consistently running AVX compared to SSE. So if you have an SSE codepath, definitely use that. Otherwise, you sort of pay a little bit of a penalty for translating AVX code. But that is obviously overshadowed by the massive performance gain that we saw compared with Intel. So this thing consistently outperforms Intel AVX code. So this is not even SSE code, which actually is much slower, of course, in modern architectures. So in the best Intel AVX code, the best timings that we see, Graviton2 outperforms that by 30%, which is actually very, very surprising. So of course, we immediately begin to ask, why is it perhaps a memory bandwidth, right? Because Neoverse N1 and mostly ARM is known for just very efficient memory architectures, and basically just a few amount of cores, it gets sort of get a very large memory bandwidth. So what we did is we ran like a scaling test on a very large node. So this node has 64 cores, which is the entire basically the entire Graviton2 chip. And then we're just running workloads, which has 16 threads. So we're just using 16 cores for each of these simulations. And then we're running simultaneous simulations. And what we should see if we're taking advantage of memory bandwidth heavily is that as we get more simultaneous workers onto this node, even though there's it matches up the cores perfectly, the memory bandwidth needs to be sort of equally distributed. So we should see performance suffer quite a lot as we add more parallel workloads. But we don't really see that here. As you can see, it's almost a perfect scaling. In this orange here, we're running 4 workloads, and it's still sort of just within 5-10% of the just one workload. So we don't really think it's the memory bandwidth. What could it be? Well, I think it turned out to be the hyperthreading, actually. So I think it's the lack of SMT. So this sort of plays a bit into how cloud providers sell compute, right? So they typically sell them by vCPUs, which in the Intel AMD dominated world, we typically think of as hyperthreads. That's what each vCPU came to mean, just SMT cores. But of course, Neoverse N1 doesn't have it, and mostly ARM doesn't have it. Most RISC instruction sets, RISC architectures don't have it, right? So AWS is kind of forced to sell, vCPUs as physical cores. So and typically you are sort of the price bracket is determined by these vCPU counts. So a 16 vCPU instance is sort of at the same price almost the same price no matter what architecture it actually is. So the result is that with the same amount of money, for Intel, we're getting hyperthreads. We're just getting 8 physical cores for 16 vCPUs. But on Graviton2, we're getting 16 actual cores. And if you look at, we take that one large node and we just take the Intel machine and we pin the workload to 16 physical cores, you can immediately see that the AVX2 score now actually wins against Graviton2 by about 10% or so, which is actually what we normally would expect to see. And the SSE code actually performs on par with Graviton2. So it actually did a very good job. It is very on par with the latest Intel Cascadelake Xeons. In terms of SIMDe performance, 128-bit. And of course, it suffers a bit for not having 256. But the fact that AWS is selling physical cores, whereas for Intel, they're selling SMT cores. That is a big factor, I think, in all of this. And of course, you can see if I pin it to logical cores again, the runtime goes back to losing out to Graviton2 by about 30%. Okay, so finally, because we're a commercial enterprise, this has quite a bit of an impact on our production cost. So I just like to summarize on what that means. Obviously, with cloud compute, even though we are doing HPC, but because we're doing cloud compute, we rent CPU by the hour, of course. And then so faster compute actually does mean cheaper. And actually, what AWS has done is it actually prices Graviton2 vCPUs. On a vCPU basis, it actually prices it cheaper than Intel. Okay, so it's already faster, and also per core, per vCPU, sorry, it's even cheaper. So that cost effectiveness just sort of compounded, right? So you can see if we translate it to what an actual run would cost, so which is, you take that timing and you multiply out to, a number of iterations that we typically do, which is about like 200 or so. And then multiply that with, the number of these simulations that we would do. So like 500 batches of data that we would run simultaneously. You add all that up. So on-demand cost, we are, about 50% cheaper running it on Graviton2 compared to running it on Intel. And it finishes faster. So it's actually quite amazing that ARM has sort of caught up to this point with just Neoverse N1. So that makes us really excited for what Neoverse N2 is going to bring. So that's the story of on-demand compute. So of course, because we're sort of running batch workloads, so we're using spot compute, and that's actually more complicated. And I think that's mostly because Graviton2s are really, really popular. So the spot prices for these are actually more expensive now than the Intels, at least for this short time. Interestingly, so this sort of price advantage goes away when we look at spot prices, but the performance advantage is still there. So which means we do still save quite a bit of money running it on spot compute, like we typically would do. Okay, so finally, just a summary observations on this talk. So we see that SIMDe translation penalty for AVX code. Firstly, we found out it's roughly about 15%, and that we can find that out because we have, again, both SSE and AVX code paths. So we can make this kind of comparison. So I think that's an interesting data point there. In our experience, it was very straightforward to compile hand-tuned Intel SIMDe for Neon, using SIMDe everywhere. So I'd like to thank all the authors for that package. It really is awesome. And of course, SSE to Neon, for which a lot of which has been incorporated into SIMDe everywhere, as far as I know. And again, if you're running on GCC and you're using older versions of SIMDe everywhere, even maybe newer versions, I don't know, but watch out for floating point contractions that may sort of ruin your day there. And I checked the floating point semantics and the flags that normally was set in the Intel, and they're the identical to the ARM's floating point semantics. That's sort of by luck, but it's not that reason. And then obviously, so I think the biggest takeaway is this very interesting cloud compute economics happens here when it interacts with sort of the lack of simultaneous multi-threading traditionally associated with RISC architectures and ARM in general. With Neoverse N series not having it. And then the AWS is forced to sell, actual physical cores now, right? But they're still, they're still selling it by vCPUs. So that basically just means that we are all been getting sort of twice the amount of physical cores compared to other architectures. And I think that plays into a large part of, Graviton2's and Neoverse N1's reputation for performance compared to the latest generation Intel AMD cores. And I think that overall helped it, definitely. And that's part of the story. And I think that's very interesting in that how it's evident here, and we can sort of see it very clearly. So that's it. That's all of our learnings. Thank you very much for your time and attention, and I hope you have a great day.